Our speaker this morning is Ryan Dalgleish. He's the Chief Operating Officer of the Air Barrier Association of America and has been involved in building envelope and building performance areas of construction in both commercial and residential sectors for over 20 years. Ryan is a trainer, facilitator, and has performed a number of management roles over 2 decades. He is actively involved in research, training development and delivery, certification management, and helping industries increase their professionalism. Ryan is a certified net zero building instructor, teaches master builder courses to builders across the country, and is a frequent speaker at various technical presentations dealing with the building enclosure to various building official associations, city departments, building enclosure councils, and chapters of the American Institute of Architects. Please join me in welcoming Ryan.
So good morning, everyone. I'm from Winnipeg, Canada, so just up the road. So I apologize to all those Minnesota Wild fans. It was tough for you last year, so I do apologize. So I'm going to go through kind of a whole bunch of stuff today in regards to putting together construction documents, but kind of delve into a couple other things that we've been working on in regards to some of the research that we've done that can maybe help drive some of your decisions when it comes to specifications. So there'll be kind of a lot of information I'm going to throw at you over the next hour and a half. If people are interested in getting a copy of this presentation, just come see me after, give me a business card, and then I can upload it to Dropbox or something like that and get it over to you. Did anyone happen to come to my session last year on air barriers? A couple people? All right. Be prepared to be disappointed again. All right. So ABA is a continuing education provider with AIA. We also, a lot of our courses are GBCI approved, so you can get your GBCI credits. This one is in process right now, so it isn't available, but it will be shortly. So I'll just go through the typical stuff. So I'm going to take a look at some of the code requirements, material performance requirements, some of the key language you can have in your specifications, talk a little bit about installation and some of the site functional testing you can perform to confirm that you have an air barrier or a certain level of air tightness. So I'll just go through. We're going to look at the code language of IECC 215 and ASHRAE 90.1. Most states reference either of these two. A couple of them will have their own energy code requirements. I know Minnesota, from my research, references IECC, but also has amendments specific to air barriers. So I'm going to go through those. Take a look at the various test methods. So how do we actually test these materials to meet performance requirements, to meet code or what your specifications might require? Take a look at the wall functions that we have. It's very rare that the air barrier is only doing the air barrier. Typically, it's at least doing the water-resistant barrier, sometimes your vapor barrier, and sometimes it's your continuous insulation. So it's very rare that we're only talking about air barriers, and it's hard for me to delineate between air and water because they're so intertwined. So even though we're talking about air tightness, it really has to do with water tightness and water management of our envelope systems. Take a look at the different 3 parts in a specification and some of the language, and then look at some of the coordination issues and some of the issues with quality assurance. So I'm going to start off with some of the code requirements and look specifically at the 2015 IECC, which I believe what Minnesota references with amendments. We'll take a look at ASHRAE, and the reason why I have ASHRAE in there is there's some lean or green rating systems that reference ASHRAE 90.1 for their energy performance requirements. So if you look at something like LEED and some of the other ones, they don't have an energy requirement per se in there other than referencing other documents for energy efficiency, which could be ASHRAE 90.1 or it could be IECC 215. Both of these are fairly similar, but there are some key differences between the two of them. And then the biggest question we get is in regards to fire, NFPA 285, and how does that impact our wall assembly when we're using exterior plastic insulation or an air barrier that is combustible. So 2 questions I usually get, NFPA 2D5, and permeable versus non-permeable. If I can answer those 2 questions, I could retire. So if we look at IECC 215, there's 3 compliance paths that you can achieve for air tightness. So you have the material aspect of it, taking a look at assembly, or taking a look at a whole system, and so you have your choice within the confines of the code to say I'm doing A, B, or C. Now, with these, they are very different in regards to what you get when you request one of these as your code compliance paths. So taking a look at materials, the test method, and I'm going to go through these different test methods, is ASTM 2178. The performance requirement is 0.004 cubic feet per foot square. Don't worry necessarily about these numbers. They're low. That means these materials aren't going to leak that much. So don't get too hung up on, other than we have a number and it's got to be below it to meet our code requirements. In the code, it actually lists specifically certain materials. So it says in there, I don't care what this is. We are going to assume these things are airtight, and so as long as you pick one of these 16, then you're good, as long as you seal the joints. If we go the assembly path, this is kind of where we take a wall assembly and put all the components together. And I'll walk everyone through that. So they say, well, you can have an attested assembly. You'll notice that the number goes from 0.004 to 0.04. So sort of 10 times as we go to an assembly. And then it does have a couple assemblies in there that it specifically calls out. And then we can do the whole building air tightness testing using ASTM 779, and it's 0.40. So if you notice a pattern, 004, 0.04, and 0.4. So all in increments of 10. Does anyone know why we have increments of 10? Does anyone know where numbers come from in regards to codes? There's 2 places they come from. There's one on the back side that I pull out, and then the second is typically around a table with a couple beers and a napkin. And it's amazing, the more decimals you have, the more believable that number is. So 004, you're never going to question it because it's got 3 decimals. So anyway, it's times 10 material assembly system, because they figure as you go and add more components and you have connections and all this stuff, it's going to leak more than just that single material. So here's that long laundry list of materials that the code says is okay in regards to meeting code requirements. So you got built-up roofing, you got closed-cell spray foam, you got cement board, interior, exterior gyp board. I'm not going to read through of all of these, but in essence it says use one of those materials and you're good. When we get to some of the other things, and the language is going to be fairly similar between state energy codes, IECC, and ASHRAE 90.1. So it says it has to be continuous. It says that it has to be sealed and joints dealt with when it comes to changes in materials. It has to withstand pressures. Penetrations have to be caulked, and then recessed light fixtures. They have to have a certain air leakage rate or seal or gasket. So it says use this material, and then you have to install it to make sure it's continuous. That's really all this is saying. It's not telling you how to do it, it's just giving you some information. So when I pulled up the Minnesota amendment to the IECC, and I'm relying on Google for this, so I don't know if it's 100% true, but I noticed a reference to IECC, but then I also noticed an amendment. And it's going to be a little bit hard to see, but the amendment kind of takes out any of the performance requirements for the materials assemblies or the whole building or tightness. So it talks about that you need to have it. It has to be continuous, it has to be sealed and so forth, but it's actually a bit of a watering down in regards to what some of these code requirements are in other states. So this is what I found. If this isn't correct, blame Siri or Google, but air barriers in this state, it looks like it's been a little bit watered down from what the requirements are in some of these code reference documents. If we switch to ASHRAE 90.1, which there's some green rating systems that reference, it's going to be fairly similar to the ICC language. but there will be some subtle differences. So it references a little bit more about being continuous and actually clearly identifying these things on construction documents. So with ICC, you don't have to worry about detailing here. You actually have to worry about detailing your air barrier and airtight connections from a code standpoint. So very similar, you got the material, you got the assembly, and then you got the whole building air tightness test. Some of the subtle differences are underlined and bolded. So you can see we have 13 materials versus 16 for ICC. For the assembly, 2357 is the main one that the industry uses, but they use 1677, 283, and 1680. So it doesn't make life easy when you have all these options of different test methods that actually give you different numbers. So if you tested a material and an assembly to all those different test methods, they're actually very, very different, and it's hard to actually compare apples to apples. So the one thing I want you to take away from here is rely on ASTM 2357. That's the most up-to-date and relevant test method for air barrier assemblies, and also the best code compliance option you have if you don't go down the path of whole building air tightness testing and blower doors and all that sort of stuff. But we'll talk about that a little bit later. From the acceptable materials, I've just struck out the ones that they have taken out. So they've gone from fully adhered to put single-ply roofing membranes. They took out fully grouted concrete block, aluminum, solid or hollow masonry construction, open cell spray foam, and so forth. The one that is typically an area of confusion is what is the air tightness layer in the roof assembly. So there is a specific reason why they put fully adhered single-ply roofing in the ICC because of some of the issues related to air tightness of roofing. And usually there's two ways to make the connection to the roof. You're either going onto the deck with an air tightness layer or vapor barrier, or you're tying into the roof membrane on the top. Now, those are two very different strategies and very different complexions in regards to how to make some of those connections. So this is saying if you do have a single-ply roofing membrane, you need to tie into that, but it can't be a mechanically fastened system that is going to be able to bellow up and down in regards to in air leakage. So in the case the air leakage isn't going from inside to outside, the air leakage is going from in the building underneath the roof system back in, and you kind of get this pumping effect when you have a mechanically fastened roof assembly. So that's why that fully adhered was in there. So ASHRAE 90.1 at this point, with some of the updating code requirements, are actually looking at making whole building air testing mandatory. So right now it's a code compliance option. They're looking at making it mandatory in the next code revision. There is one or two states that require whole building air tightness testing. I was in the state of Washington last week, and so it's going to be required on all commercial buildings over a certain amount. Some building owners like the Army Corps of Engineers or some GSA, General Service Administration projects require it as a mandatory code requirement. Overall, you don't see it as much. The code compliance option typically is the material or assembly, but I think going down the road, you're going to see verification in regards to requiring whole building air tightness testing. And there's some complexities around that, and I'll talk about those a little bit later in regards to how that's going to change your specifications, your construction process, and maybe some of the things that you need to do. So there are two standards that they reference, ASTM 779 or ASTM E1827. Again, don't worry about all these ASTM standards. There's all these numbers, there are all these things. You don't have to worry about memorizing them. It's just a way to test a building. And 2 weeks ago, there was at ASTM a new air tightness standard that will then be referenced in the code. So these are going to go away a little bit in regards to the air tightness testing. Now, when we choose air tightness performance and say want to look at whole building air tightness testing and making our envelopes tighter and tighter and tighter, people go, why? You know, why do I want to go to increase Air tightness, why can't I just do the bare minimum? We haven't had problems in our buildings and we're just good. And what we found is that quantifying that energy savings or energy efficiency and what that means has been these random numbers. So again, there's two places we get numbers, and I'm sure this came from one of them, but the US Department of Energy says, well, if you put in an air barrier, you're going to save 40%. And some say you're going to save 82%. And some say you're going to save 20%. So the question always is, if I make my building tighter, how much energy am I actually going to save? Like, how much for my building in this climate I'm actually going to save? And so that was a question we were always getting, and we couldn't come up with an answer other than the two ways I mentioned. So we said, let's put something together that maybe can help quantify it for a building owner or design team to say, if we go from this to this to this, what does that mean in regards to monetary savings and overall energy savings, and what would we see in regards to overall energy efficiency? So as we go down the road of net zero and net carbon and regenerative buildings, the air tightness tends to be the low-hanging fruit in regards to increasing that performance. So if people are familiar with passive house and things like that, it's all about air tightness. It's all about big insulation levels. And you're going to notice going forward when it comes to net zero, they're always going to be super tight envelope, super insulated envelope, nice mechanical systems, some type of renewable energy, and we'll get to that net zero. Or start designing net zero ready buildings for addition of renewables later on. And we've seen that, at least where I'm from, some of the more leading builders going down and getting net zero ready because of the cost of some of the renewables when it comes to solar voltaics or geothermal energy or things like that. So I'm just going to walk you through some of the background in regard to this tool, and this tool is a free tool that we've developed with Oak Ridge National Labs and the US Department of Energy, and it's basically an energy calculator. So it allows you as a user to input some basic data for a project, for a location, and then you're going to get a number out. And you can go different levels of air tightness to go, what are my savings? So this was a study, this was done a little bit, I'm going to think about 5 or 6 years. And there was a study done by these different bodies. So NIST was the National Institute of Science and Technology. You had the Army Corps of Engineers. The Army Corps of Engineers has been one of those building owners that is really focused on building air tightness and energy efficiency. Some by Pennsylvania State University, and this FCEC, which honestly I don't even know what it is. And so what they did is they took a look at both existing buildings and new buildings being built. So, buildings that have been around for 20 years, 10 years, maybe even 5 years. And they took a look and said, well, what's the average air leakage that we get? And this is in metric, so I apologize for being Canadian, but don't worry too much about the numbers. What they found is that you're about almost an 8 liters per second per meter squared, and the code's at a 2. So you can see where that average is here and the code is here. Now, usually the code is, the bare minimum, what you have to do to not go to jail. So we have this big discrepancy between where we're building our buildings now and what the code actually says. What we found is that as we go lower and lower, it's been shown that we can get down to lower and lower numbers. But this was kind of the base where we went to. We needed a base to say how leaky are buildings now. If we tighten them up, what is that going to mean? So we put together a program, and as we looked at it, again, we couldn't really delineate that air from moisture. So we're like, can we go and have an energy calculator, but then also have a moisture calculator at the same time that can indicate how much moisture going through your wall assembly by air leakage can be reduced by a higher level of air tightness. Now, most people don't necessarily care as much about air tightness, but people really care a lot about moisture management in their wall assembly, because that's what damages everything. If you have a little bit of a leaky envelope, it's a bit of an energy hog. You're going to be uncomfortable, but moisture is what kills buildings, not necessarily air leakage. But again, you can't delineate those, because if you have a leaky building, you're going to have a lot of moisture going through it. So it actually does two things. So the U.S. Department of Energy, there's all these modeling tools, and anyone that's involved with green building, you know, you're modeling energy and so forth. So they took the same type of approach where they're going to put some models together based on, you know, what the average air leakage is, what the code requirements are, and where we can go. Put in a couple things that you as a user can just dump in easily, nothing too complex, and then get a number out that you can go and say, hey, is this justified to go from 2 to 1, to go from 2 to 0.5, whatever it is. And there's some places where maybe you're like, it doesn't make sense. If you're in some of these kind of states that it's not super hot or super cold, things like that, you might go, it's not worth the extra cost or whatever to go to this higher level of air tightness, which is fine. Now, typically, once they overlay that moisture thing, then they're going, oh, I guess we still need one, and maybe we do go for an increased air tightness level just because of that moisture management strategy. So I'm just going to walk you through a little bit. Now, this is Department of Energy kind of looked at the prototypes of buildings across the U.S., and they said, here's the majority of buildings. And so we couldn't do them all. We just started with the top 3. So we have standalone retail, mid-rise apartment, and median office. And that equals about 29% of the building stock. So we couldn't do everything, so let's start with the building types or architectural types that are traditionally used across the U.S. and have those as part of our energy calculator. So this is the interface for you. Now the moisture thing is just being added right now, but all you have to do is enter stuff on here and you can get a number. So it has where the location is, the building type, you put in the square footage, you put in what you want that air tightness level to be, and then you get a number. So you could probably do this in 60 to 90 seconds. Even if it's not 100% perfect, you'll at least have some idea in regards to what air tightness is going to do for your building. And so you'll get a report, and it's going to show 1 year of savings based on current utility data. So that would be taking utility data from Minnesota, whether it's electrical or natural gas or whatever your energy source is, input them into the program, and then you'll get an actual number in regards to monetary amounts of energy savings through air tightness. And then you'll get the number of how much actual energy you saved in kilowatts or whatever the fuel source is, and go, is there some type of return in regards to doing this? And it's going to change by climate. So I find that the colder the climates are, the bigger the return. The hotter the climates are, the bigger the return. And those kind of really moderate climates, the return isn't as good, but it is an ongoing return that the building owner will get over the lifespan of the building. This is based on today's utility data, and most people feel that utility costs are going to go up, so then this would incrementally increase the cost savings for the owner. Now this is the moisture part laid over it, and this was taking a look at 3 different climates, one being Miami, so very hot and humid, the second being Chicago, and then where I am from Winnipeg, and we took a look at if we had that base air leakage we talked about, that's 6, and we went down to something really tight. This is 1 square foot of envelope per year. So if you think of 1 square foot, this is saying you're going to have 18 pounds of moisture going through that 1 square foot in a year versus 1.3 in that same 12 inch by 12 inch area in regards to the amount of moisture going through by air leakage. So this doesn't deal with diffusion. This doesn't deal with you just building a bad building and water pouring in. This is just the amount of moisture going and being carried by the air and then condensing or going in your wall system. So the tighter you go, in this case, it's shown that you can actually reduce the moisture going in your wall assembly by 14 times. So maybe it's not the energy that you care about, maybe it's the moisture and issues with moisture within your envelope that reduces, the effectiveness of your insulation and rots components and all that sort of stuff. And so this is typically what gets people's attention more than I'm going to save a little bit of money or a lot of money, because they know this costs a lot if you have to start ripping down exterior facades and deal with rotting components of steel studs or wood frame construction or whatever that happens to be. And then you can go through and look at different building types in regards to, and this again is just an example from Chicago in regards to retail, medium, mid-rise apartment, in regards to what those numbers can be. And we find that retail is usually the worst. Mid-rise apartment usually isn't the greatest. And median office typically isn't too bad when it comes to air leakage. And again, this happens to be Salt Lake City just because I presented in Salt Lake City. So when you go to our website, airbarrier.org, so if people aren't familiar with the association and the resources, we kind of dump everything on our website, and this is exactly where you can get the information. So you just go to our website. Under technical, there'll be energy calculator. You can open it up and you can start inputting your data. So just a note, the moisture thing is being added right now and will probably be ready in about a month, but you can go in there right now and at least look at the energy savings monetarily and energy use in total and get some numbers. So you can maybe even play around with some of the projects you have to go, can you justify a higher level of air tightness? So the question becomes, well, you know, how does that impact me per se? How does that impact our specifications? Well, it can provide some guidance in choosing an air tightness level, whatever that happens to be. It can provide justification for an owner to go, is it worth the extra cost? And typically there is an extra cost, but sometimes it's very minimal, sometimes it's a little bit more. And the tighter you go, then the more stuff that you need to have in place to make sure you actually meet those air tightness requirements. So that might be whole building envelope commissioning, whole building tightening, air tightness testing, having some form of credentialing or qualifications for your contractors that are doing this work, and probably spending a little bit more time in regards to putting together your construction documents from a specification standpoint and a detailing standpoint. So just because you pick a number doesn't mean it just randomly happens. You have to be very deliberate in what the things that you do in regards to meeting that air tightness requirement. Has anyone ever watched The Office? Michael, yeah, remember when he declared bankruptcy? What did he do when he declared bankruptcy? He literally went, I declare bankruptcy. He's like, oh, that was easy. It's the same thing with air tightness. You can't go, I declare air tightness, and it randomly happened. You have to be very, very deliberate in your choices and how you sequence things. And typically where things fall down is in the installation. You know, you can get really good design, you can get building envelope commissioning, but usually where things have a bit of a disconnect is when you actually get on site and start putting these things together. You know, when you have the air barrier installer doing his stuff, the curtain wall installer doing his, the roofing guy doing his, and then who's responsible in making all those connections to make it airtight. So we did another study, and this was taking a look, this was with the Army Corps of Engineers. And just because they've been doing it so much and they've had so many buildings that have gone through it, and they did a bit of a survey of the buildings they've done. And they looked at ones that had some type of QA, QC, and ones that they're just like, let's see what happens. And what they found is all the ones that had some type of QA, QC, you met it 100% of the time. If you randomly thought, like, let's just see how things go and test it and see if we make it or not, you had a 2 out of 10 meeting performance. So you had a 20% chance of meeting the air tightness requirements if you didn't have any QA, QC. So it's going to be dependent on how lucky you feel in regards to choosing that air tightness level, whether or not it's going to make a difference. So there is some value in putting these things in place because it's kind of hard to meet really, really tight buildings without a lot of stuff happening and a lot of stuff happening right. So how does this impact your specs? We're doing some more work to add more architectural types. So high-rise apartments, hospitals, secondary schools, large hotels. So now we'll have 7 prototypes of architectural types that you can choose from and should knock off a lot of the projects that you're working on in regards to this calculator. Again, this should be done in about a month. Don't hold me to that because we're waiting on U.S. Department of Energy in Oak Ridge to actually get this done. So now you're going to have this nice database of architectural types and climates and things like that that you can use. All right, fire. Has anyone had a question about NFPA 285 ever? Does it give you heartburn? This is a big question that we always get, and it's an expensive test that has to be done. The issue with it is you have so many material choices and things that you can put in your wall assembly that it's never really a simple answer until you have a lot of information. And sometimes it's required and sometimes it's not. And sometimes it depends on the insulation you use and the air barrier you use and the height of the building and all these things to say, do you actually have to have this test to meet the building code? So this isn't in the energy code side of things. It's typically just in the building code or the international building code. And some of the requirements was this because we started using exterior insulation that was extruded polystyrene and expanded polystyrene and polyiso and all these cellular plastics that burn, right? These things do burn. They do off-gas things when they're burning. So this was something that as we moved to exterior continuous insulation, we had to deal with. When we put everything in the stud, it wasn't an issue. When we started moving everything to the outside because it made sense from a code requirement and from a thermal bridging requirement, it then added some complexity of our exterior wall assembly. There are also combustible exterior claddings, and there are water-resistant barriers or air barriers that can be combustible. Some of the older technologies, like the old self-adhered membranes, they'll burn and they'll melt and different things like that. So this is just a bit of a picture of the test. And think of just a big wall. You start a fire in the inside, it burns for a bit, and then it comes out of that window opening. And then you're seeing, well, how far up that wall does it go, and what does it do in regards to burning of the materials? And usually it all has to do with time. So how long it takes to burn so people have enough time to get out. So if your building's on fire, just because you have an NFPA 285 assembly test doesn't mean your building's not going to burn. It just means that your building's going to burn at a rate that it gives people time to get out. So it's all about health and safety. We had that big issue over in the UK with the towers there, the Grenfell Towers. You can see how this is really a health and safety issue. And this is a big question that people get of what way can I do my wall assembly to make it compliant. So because it's an assembly test, you're not able to kind of like swap things out. And so if you have a test with these 10 materials, you get a number, you pass, you fail, whatever it is. Now, if you change one of those materials, it's not the same assembly. So you either have to get another assembly tested, or there's sometimes where you can swap out materials if you have an engineering judgment lever that you can get acceptance by the authority having jurisdiction. Usually the way that works is they look at the component you want to switch and go, is this more flammable or less flammable than what you're swapping out? So if you're going in a swap out component A, it's less flammable, you can get an engineering judgment letter and then get code acceptance by the building official. He still has to accept it. It's not a given. They don't necessarily everyone accept engineering judgments, but it is sometimes a possibility to meet some of those code requirements. Now, some of the assemblies passed, but once we put an air barrier in it, it actually failed. And when I first heard about the NFPA 5 test back in like 2006 or 7, because I got a call from a general contractor in Wisconsin, and he's like, the guy's asking for my NFPA 285 test on this air barrier. I was going, well, what are you talking about? I'm like, this little thin thing is a big deal in a wall assembly. And what we found was that some of them can be an issue in regards to combustibility just with this thin little layer of air tightness that we're putting in our wall. So there's a couple different things, and these are some just references that have been provided to me by some of our members. I'm going to skip over 2009 and go look at the 2012, and I found this to work well. Going, is it required? Well, is it type 1, 2, 3, 4? If it's not, then you don't need it. If it is, you move up going, do you have plastic insulation? Yes or no? If no, is your water-resistant barrier combustible? If no, then you don't need it. If it is plastic insulation, then you go, is it more than 1 story? So there's this kind of matrix you can work your way through to go, do I need to have this test? So it's your insulation, it's your wall air barrier, it's going to be your height of the building and type of building that will indicate whether or not you need it. Now, most air barrier manufacturers have been involved with or have done their own testing to NFPA 285, and they'll have them listed. Some of the changes that I've seen is with self-adhered membranes, sometimes they'll put on like almost a metal facer to it. So it's the same sort of bitumen-based membrane with a metal facer. Some of the fluid-applied materials have had to put fire retardants in it and so forth to meet those requirements. So there's kind of like 4 things you need to figure out whether or not you need the test or not. But a lot of confusion and a lot of complexity to this requirement. So let's take a look at some of the materials and test methods and just go through what it means. So if we look at the key requirements for an air barrier, we know it's got to be air impermeable. We know it has to be continuous. We know it has to be strong, resist loads, and we know how it has to be durable. Now, what do these mean? What does a durable material mean? What does strong mean? What does continuous mean? Those are all things that we need to take a look at and understand, because there is more to air barriers than just it leaking a certain amount of air. Does anyone know what the minimum, like what the first air barrier material was? Gypboard, right? So gypsum board was the first air barrier. And ironically, that is, the testing of that material is what's in the code. That 0.0004 is how much that exterior gypboard leaks. So again, I don't know, I think, guys sitting around going, well, that looks tight, they picked it. And anything that's tighter than that, that's good, and anything that's not as tight as a piece of drywall doesn't meet air barrier requirements. So that's where it came from back in the late 70s, early 80s, where they said we need to make our buildings a little bit more tight, and so we're going to use drywall. And it was traditionally used in residential construction. So you took drywall and you took some gaskets and you took some sealant and you took other things and you made this system. And there is, if people are aware with Building Science Corp, Dr. Joe Stiebrick, he's got this paper on the air tightness approach of drywall. And it's got details and things like that. And some of those things are used today in regards to meeting air tightness in residential buildings. So the material itself, again, let's not worry too much about the numbers. It's 2178 and it has to meet this number. And what it is basically you're taking this 1 meter by 1 meter piece. So imagine you at home, you get this 1 meter piece of fabric or whatever, get your shop vac, blow on it, go on the other side and see how much is leaking through. That's really all it is. It goes into this fancy thing and it looks all cool, but really all it is taking a look, creating a pressure, and going how much is leaking through it. And then all you do is report a number. Now, does anyone know what that is? Take a guess. Peanut butter. I guess I should have looked at the slide before I asked what it is. It literally says it. So this is that same 2178 test, 20 mils of peanut butter, and it met the code requirements. Right? So when I went back to when I was talking about the code saying, well, here's this material compliance option, there you go. I've met the code. People laugh, but I'm like, someone's going to do it. So then they're like, well, how do you make this an assembly? How could this be an air barrier assembly? I was like, you can get some jam, and you get some bread, and you'll have this whole air barrier assembly. So anyway, long story short, do not put all your eggs in the basket in regards to, I'm going to go the material compliance method. Because this is really what you're getting, right? This is really what you're getting. And if you look at the other code requirements, it has to be durable and strong and stuff like that. I would say that that isn't durable or strong or so forth. But it drives home the point that that's not a great test. So one of the things with air barriers is they have to be able to be continuous. And everyone thinks, well, that's basic. We know that. But this building's going to move. It's going to change in regards to, it gets hot and cold. It gets wet and dry. As that happening, the building's always moving, seismic or whatever. So the air barrier, to be continuous, has to deal with those things. So it typically can't just be this rigid thing. It has to be able to move with the building and deal with those different variations. And then we have to make it continuous. So we're going to have our details between foundation and walls and windows and walls and different wall systems, roofs and walls, interior floors, and so forth. And there's two that I want you to really pay attention to out of this list. And the two are the roof wall and the wall and window. The wall window leaks the most often. The roof wall leaks the most, like the biggest amount of energy or biggest amount of air leakage. So when we've been involved in some forensic investigations, your window wall and your roof to wall are the two details that you should put the majority of your time in, because that is where most of the stuff is leaking. And a lot of times it's because you got a couple different guys working on it. And so you got a roof guy, you got a window guy, and then you have this by others. Has anyone heard of by others on drawings? Right? I don't know who this by others is, but he's going to be pretty rich because he's on every project. In reality, it's like you got the air barrier guy, he stops here. You get the roofing guy, he stops here because that's where his scope of work ends, and there isn't necessarily that connection. So two things to focus on: roof to wall, window wall, and there's big differences between wall and curtain wall and wall and storefront and wall in punch windows too. And if you're going to do some type of site quality control, put all your effort into here. The air barrier doesn't leak in the middle of the wall. It's always going to leak where you have these connections. And as we start getting things punctured through it, whether it's mechanical, whether it's plumbing, whether it's whatever coming through, we have to make sure that it's airtight. The issue with this is typically the air barrier guy is gone. He does his stuff, he does this great job, and then everyone punches holes in it after, right? And he's gone, he's not coming back. So the construction manager or general contractor has to be aware of that, and all the other trades who don't know air tightness, and our electrician doesn't wake up in the morning going, I'm concerned with making this building leak, or a plumber or whatever. So someone has to be there to coordinate that and to make sure the stuff is sealed after the air barrier guy leaves. So this is that assembly test. So the material test was just that 1 meter by 1 meter little thing, and you kind of blow on it. The 2357, which is the code compliance option number 2, takes a look and looks at an 8-foot by 8-foot specimen. And it puts in a window, and it puts in mechanical penetration. It has some masonry ties. You'll have seams and joints. You'll have round penetrations coming through, and so forth. And it says, go and put your air barrier system on here. So it's not just that one material, it's your air barrier, maybe your sealants, transition membranes, whatever that happens to be. Put it on this wall, and then we're going to test this wall. So this wall, to me, is much more realistic in regards to testing material to make sure it's okay, and putting those components together to go, is this whole system going to leak so much? So this is just kind of a little bit of a picture of what it looks like. They're kind of going through the process right now. So there's 2 specimens. This is just one of them. So you go and you put in your air barrier on it, and then you go and you do your testing. So with this test, it actually ends up having higher loads to simulate peak wind loads, loads from stack pressure, loads from wind, loads from other things, to make sure that it's okay. So it kind of takes the material, it beats it up. You know, there's 2,000 cycles back and forth, positive and negative, wind gusts, all this sort of stuff. So much more realistic than this 1 meter by 1 meter, little bit of pressure and measuring it. This is more real life conditions, and what I would hang my hat on if you didn't want to go down the route of whole building air tightness testing. Okay? And I would say every manufacturer that has an air barrier, any good air barrier, has all done this testing. So this isn't something that's special. The one thing that I tell people to keep in mind is look at the materials they actually used to pass that test, and take a look at requiring those same materials as part of your specifications. Because they may do the test on the air barrier in certain transitions, and then it's specified with the air barrier and all these other transitions and sealants that maybe weren't tested, so you can't be 100% confident that you're going to get the same types of results. So this should be a minimum in regards to your requirements and your specifications. Durability. This is something that is debated. We don't necessarily have an answer now, but for the most part, we're putting these things in our wall, and they're being buried. They're behind insulation, they're behind our masonry, they're behind whatever, and it's not easy to fix these things. So the question becomes, if we're putting an air barrier in, is it going to last as long as the building's durable life or the life cycle of the building enclosure assembly, whatever that happens to be? So 30, 50, 75, 100 years, is this thing going to work for that amount of time? And so, there's other things that we need to consider other than just air permeance. So we've just talked about blowing air on a wall and measuring it. The air barrier has to be much more durable than the peanut butter example. So if that's the case, we have to go and look at other testing that can be done to make sure that this material is going to have the ability to withstand movement, to be able to bridge joints, to be able to deal with moisture, to be able to deal with other things that are really going to play havoc on it in regards to the longevity of it. If anyone is using exterior continuous insulation, you've gone a long way to helping to protect that air barrier, because you get away from those cycles of hot and cold. So if you don't have exterior insulation, just know that the air barrier is going to be under way more stress than it would be with exterior continuous insulation. A lot of people are designing that way. A lot of codes are requiring that. So the default of that is you now are protecting your air barrier from losing its durability over time. So what the association's done is put together a standard for these air barrier materials that goes beyond the air permeance testing of materials and assemblies. And we looked at all the different types of materials, and we don't have it for absolutely everyone, but I would say we have it for the majority. So we have it for self-adhered membranes, liquid applied, medium density spray foams, board stocks that'd be using like exterior insulation and taping the joints, factory bonded membranes to sheathing. That's, you have these boards coming out with pre-installed air barriers on it now and just detailing the joints, and then the traditional house wrap. So we've gone through each of these materials and said, what are the physical properties that these things should exhibit to make sure that they provide some type of durability? And so we've come up with this kind of list, and it's a little bit different by product, but we look at pull adhesion, so how well is it actually sticking to the building, its water resistance, because these guys are, or these materials are providing the water resistant function, then they should be able to resist water and water penetrations. We make everyone do vapor permeance so people can determine whether or not it's going to be their vapor barrier layer or not. Crack bridging, so this is just an example of some of the things that we do. Some of the ones that we are working on right now are non-insulating board stocks, so that's kind of some of these new systems that have come out that is exterior gyp, and you're just detailing the joints, so we call that non-insulating board stock. There are a couple of those products on the market today, so we're developing standards for those. And then engineered polymer films for interior application. That's just a fancy way to say poly vapor barrier. There's a smart vapor barrier that changes with the amount of moisture, relative humidity. Its vapor permeance goes up and down. So that's the one that is being worked on right now. So if you actually go to the ABA website, under technical information, we actually have a listing of all the materials that have gone through this standard. So if you're looking at least creating some level playing field in your specifications, you can require that it has gone through an ABA evaluation, and we have it broken up by all those material types. So you can go to fluid applied membranes, you'll get a list of the manufacturers, click on the manufacturers, you get a list of the materials, and we actually publish their test results they're from their third-party testing. So it's not, a technical data sheet that can maybe be interpreted differently. We actually publish the results from the testing that's done. So it becomes a good resource that you're not figuring out and comparing these materials going, well, is this one okay, and how's it compared to this? We kind of take care of that for you to say all these materials have met that standard. So we'll take a look at developing specifications, and these are just kind of the three main points. We're going to look at what are some of the specification tools that you can have, defining some of those performance requirements in your specification, and then taking a look at some of the three-part specifications and things that we want to have in there. So for specifications tools, there's a lot out there. The association has guide specifications that we put on our website for all those materials that are evaluated. So you can go to our website, you can download these specifications, glean it, copy and paste it, do whatever you want, but it has some good language that we've developed through our technical committee that it can at least provide you a reference in regards to not having to reinvent the wheel. All the manufacturers will have their guide specifications. You'll have master spec, and then you'll have BSD spec link. BSD spec link, for people that aren't familiar with it, it's a program that is like checking boxes, and then you get a specification at the end, so you're making your choices throughout, and then you get a thing. With master spec, the one comment that I'll make about master spec is they've kind of worked on a thick fluid applied and a thin fluid applied. When we take a look at it, we go from a performance standpoint. We don't get into this one's thick, this one's thin, but master spec has done that. And it was not that long ago where you actually had this range that a material wasn't included. I think it was like 10 to 20, and then you had 30 to whatever. And so the 20 to 30, you had these materials that were just randomly not included in master spec because they happened to be in this narrow band of thicknesses. So you are going to see a difference if you are using master spec, that they break up their fluid applied into thick and thin. We don't necessarily agree with that because we take a performance based approach and not base it on thickness. So let's take a look at section 1. There's 5 things that create the most heartache for us when we go on the website or on the job site. And one of the top 5 are coordination with other trades because of the significant impact that they have. And that is from the people that are doing the substrate in the first place, whether it's the mason or the carpenter or whoever's doing your substrate, to who's doing the veneer, to who's doing the insulation layer, and all the damage that can happen after. So someone that's laying block doesn't necessarily lay it going, I got to make sure it's in this condition for the air barrier. They may or may not know unless the mason is doing the air barrier also. And again, the 2 areas would be the connection to the opaque wall to some of the other assemblies. So you have to draw in all these different sections. And if you look at the air barrier section in regards to relating to other sections, you're going to have a list like this. Because just think of all the people that are going to touch that air barrier. And there's going to have to be some coordination. We'll talk about that a little bit later. But there is a lot of issues that we run into just because of a lack of understanding of the trades and not having the general contractor, construction manager, really understanding sequence of construction and making sure it's being done in the best way possible. This is that language that I talked about using ABA evaluated materials. So we see a lot of this in architectural specifications where they have performance requirements and rather than listing all this, they just say, here you go, use an ABA evaluated material. And then they'll choose their 3 manufacturers for competitive bidding, but all of those making sure that they meet that performance requirement of ABA evaluated. Compatibility. This is a big one specifically when it comes to roof and wall, because there are so many different compositions of air barriers and different compositions of roof membranes. Some of them work well together and some of them don't work well together, i.e. they actually eat each other or can't stick to each other or so forth. So the issue of chemical compatibility between the air barrier and the roof membrane needs to be thought of. The types of sealants you use, again, needs to be thought of in regards to what's compatible with what. And the complexity comes is that you have manufacturer A, manufacturer B, manufacturer C, and they don't necessarily talk. So a lot of people that we're seeing in their specification is requiring some type of chemical compatibility letter or declaration saying this material works with this. It means the manufacturers are having to do their work and do a lot of testing, but that's fine. That helps you to make sure that you're covering yourself when it comes to those compatibilities and making sure things work. Now, there will be times where things don't work, say with a window or a roof wall connection, and that's fine. You may just need a third material to bridge between air barrier wall, air barrier roof, and then using something that's compatible with both. So there are strategies that you can use even if things aren't chemically compatible. You can bring in a third material to bridge that gap. Pre-installation meetings, this is one of the most critical things that you can have identified in your specification. You need to get everyone sitting around the table, from the general contractor and all the impacted trades, to walk through who's doing what. So we want to get away from that by others that we see on drawings and go, here is who is responsible for that final connection between the wall and the curtain wall. Who's responsible for that sealant between here, and who's doing it, and what is the sequence of construction. Some of the things that we run into when we go on site in regards to sequencing is windows being put in the window rough opening and the air barrier isn't done yet. So it's like, how are you making connection to the air tightness layer in the window that may be at the back of the window assembly? You know, so the air barrier contractor hasn't had a chance to wrap his flashing into the rough opening to make that connection, and then you're scrambling trying to figure out how do you actually make this connection. So having everyone on the same page, and this should be something that happens on an ongoing basis, and having all the trades, even involving maybe your commissioning agent, your manufacturers, and so forth, to get the sequence down right. Now, if you are using mock-ups, which are something, again, that we promote as another form of quality control, you can kind of work through some of these details in the mock-up stage, that you get the trades involved, you can go through the sequence of construction, and then you can actually test it to see if it's okay, if you're meeting your tightness, if you're meeting your water tightness, or whatever that happens to be. So having this with a mock-up, you go a long way to getting the project on a good footing or a good start to hopefully alleviate a lot of the issues that might happen after stuff starts to get covered and it becomes expensive to try to fix some of these things. So if we go at section 2, some of the things that we need to think about before we start editing that. The number 1 is, what is our material actually going to do? So as I mentioned before, a lot of these materials do a whole bunch of different things. And so if you look at a traditional self-adherent membrane, well, it's going to be your air barrier. It can be your vapor barrier, because now you have 2 choices, permeable and non-permeable self-adhered membranes. No matter what, it's going to be your water-resistant barrier, and it can be your insulation. So you need to design and figure out the material and what is it exactly doing, right? Is it just the air tightness layer? Is it just your water-resistant barrier layer? And sometimes air barriers have been used just for water-resistive, and they haven't even cared about the air tightness level. So you need to be very deliberate to say, this material is doing this. And then as you start to build your wall assembly, then you have to build all those other components in your wall and going, how is this thing going to work from an energy standpoint or a vapor permeance standpoint? So some of the things that you can put directly in your specifications when it comes to assembly, the 0.4 is what we see in that code using ASTM 779. We got that 2357, which we talked about is probably the way to go. And then putting this other language, you know, making it continuous, structural support, and all that sort of stuff. Air permeance, fire characteristics, and then additional properties. We've identified things like tensile strength. So like, do these things rip? How easily do they rip? Can something be sealed? There's that term talked about, self-sealing. That doesn't exist. Anything that punctures an air barrier isn't self-sealing. So usually there has to be something done to correct that seal. Now, it may not leak as much as you think, but there is no self-healing type of membrane that's on the market. So when you see things like, I can put a screw through it and it's self-sealing, no, that isn't true. Vapor permeance. So the second question we get is vapor permeable membrane versus non-vapor permeable membrane. And what do I use in this location with this building and so forth? And there really isn't any easy answer. It's always, it depends, because it has to depend on what is going into your wall assembly and where you are. So if you're in Minnesota, you're going to design it way differently than you might in South Carolina, but maybe you can. And there are areas where you can have a wall assembly that can really work anywhere, but you need to understand some of the control layers in that. So things to think about: the climate, where the insulation layer is, what the temperature, relative humidity of the building is going to be. And then we can use programs. Has anyone ever heard of WUFI? W-U-F-I? Yeah, okay, so it's a program where you can kind of build your wall assembly there, and it will take a look at, you know, how much moisture is in the wall assembly and if it's getting into a critical stage, or if you don't run into areas where things are really wet for a long time. So a wall can get wet, that's not an issue. No matter how well we do our walls, things are going to get wet. It's how long does it stay wet, and does it have the ability to dry, which will determine, do we have a problem or do we not have a problem? And again, it's not an easy answer. So if you're using exterior insulation, that's going to change your wall function and whether you use a permeable or non-permeable air barrier. If you have insulation in the studs, typically most people go the vapor permeable route, especially if you have like an interior vapor barrier like poly or whatever that happens to be. So in Minnesota, there's buildings that you could use a vapor permeable, there's ones that you can use a vapor impermeable, and probably all of your buildings could use one or the other. It just depends how you start to structure these layers. The best thing to do is use a program like WUFI. I'm going to say that, and I can't promote products or things like that. What I say is everyone seems to be leaning to more of the vapor permeable type membranes, just because, again, this fear of that we're going to have some type of vapor lock, and you know, the moisture is not going to be able to get out. Moisture is fine if it doesn't condense, so as long as you keep your exterior sheathing at a temperature where it won't condense, then you typically don't have too many issues. But people have been going to the vapor permeable just because they like it. They're just afraid of this sort of vapor lock within their wall assembly. But really, you can use either in a climate like Minnesota, just depending on how you start to layer your wall assembly. So with the air barrier, it's usually never doing everything. It's usually part of a whole system of all these different components. And you have to use sealants and transition tapes and so forth. So all those materials that you're using still have to be durable. It still has to be able to deal with the harsh reality of construction, during construction, and then after. And then there's a lot of detailing that needs to be done at fasteners. So we're going to take a look at some of the stuff that you're going to see in the part 3 of the specification. So taking a look at inspections of substrates, prep, transition penetrations, and installation. So things that require a bond to the substrate, typically which are self-adhered membranes, fluid-applied membranes, or spray foams, have to be able to stick to that substrate very well and not release during construction or over the life of construction. So with that being said, substrate preparation is extremely important in regards to moisture content of the substrate and just how dirty it is. So I always, I use the analogy of like painting your house. So if you're doing interior drywall and you're taping and filling it and so forth, if you do a really crappy job and paint it, you know you did a really crappy job. And so a lot of the time goes into making sure you have that nice substrate so your paint looks good and your wife or husband isn't making you redo it. So think of that as an air barrier. Your substrate has to be really good for it to be able to be properly installed. So the question becomes, so like how well do these things have to stick? And we require our contractors and our manufacturers to do testing, adhesion testing, to see how well does it stick to a building. And everyone's like, well, how well does it have to stick? And I was like, I don't really know. So we thought, let's try to give some numbers, and not necessarily that you need a number to put in your specification to say it has to stick this well, but if nothing else, we can provide some guidance going, what typically could I see in the field if I'm doing quality control of how well these things have to stick? And so because we go around, and if the architect specifies the ABA quality assurance program, we'll go on site, we'll do an inspection and audits, and so we do this testing. So we had this database of inspection reports over the past 15 years that we said, we can go and start gleaning some information out of those things and go, here we can provide some guidance to the industry. So what we ended up doing is taking a look at what requirements we had for lab testing. And in lab testing, we had a number of 16 PSI. Does anyone know where that 16 PSI came from? You all know. It's one of the two, right? I have no idea where that came from. But someone randomly said 16 PSI. And so that's a lab test. And we're going, well, if we go to the field, I would expect it's not going to be as perfect as a lab. It's not going to be under these nice temperatures and really clean and all that stuff. We're going to expect if we go to the job site, the substrate is going to be dirty and whatever, and it's not going to stick as well. And so we said, like, we need to maybe have it less than 16, but we didn't know if 12 is okay, or 10, or 8, or 4. Maybe 4 is okay. We didn't really know. So there's 3 things that we did. We took a look at updating a test method. So we were using an ASTM test method, D4541. And again, don't worry too much about the test method. It was basically just a way to do adhesion of coatings. So when air barriers started, there weren't a whole lot of test standards for air barriers. So we kind of just stole stuff from like roofing and waterproofing and coatings and things like that. So we're using one for coatings. Then we said, well, let's go through and look at what we're actually getting in the field, and then maybe start to do some investigation and doing a number. So we've created a test method, which again is on our website. You can download it for free. It tells you how to do adhesion testing on air barriers, step by step in regards to how to do it. So you can go to our technical section on our library, download it. It's good for your technical library. Then we went and took a look at all this. So we had just under 3,700 reports that we looked at, 2,400 lines of analysis by material type. And what we found is that the average PSI in median is above 20. So that's taking a look at absolutely every substrate, every air barrier material over 15 years. This is an average of what we're getting, which was actually very surprising. We thought it would be worse than what we're getting in the lab as a minimum requirement. So this kind of surprised us a little bit. And so this is just a result. There's a paper being presented in a couple of weeks that will have this that you can take a look at. So we looked at, here's sort of self-adhered fluid of pride. You can see kind of where it is. People might go, well, why is the maximum 80? A lot of the test equipment just goes up to 80, so that's the only reason why it's the maximum. And then we did it by substrate too. And you can see, again, it was kind of surprising that the substrates, there wasn't a huge variation. The one that we knew would be the worst is glass-faced gypsum, because usually when you actually do adhesion testing on it, you end up ripping the facer right off because the air barrier is so stuck well to it. If you're putting it on things like concrete or steel, it sticks super well. So what do all these numbers mean? Well, if you want, you would at least have some guidance if you wanted to put a performance requirement in your spec. And if not, if you're like, I don't want to pick a number, at least you have something to reference if you're doing site quality assurance. So if you have a building envelope commissioning agent, if you have an inspector or whatever, you'll get numbers, and if it's like super off, then you'll go, hey, there was a study done, the average was 20 and you're getting 5. Something's just not right. So it at least gives you a reference based on some type of research other than the 2 other methods that we get for achieving numbers. So when we aren't adhering it and we're doing some mechanical fastening, the substrate prep's a little bit easier in the fact that we just can have like stuff poking through it, and that we have a good surface that we can actually start to mechanically fasten these things. When you are using fasteners going through like a house wrap or board stock, you have to be very careful in regards to the type of screws and washers and things like that you're using, because all manufacturers will have very specific ways to mechanically attach it if it's performing the air barrier function versus just performing a water resistive function or exterior continuous insulation. So if you decide to use extruded polystyrene as your air barrier and you're going to treat your joints, there's going to be very specific types of fastening you need to do and very specific types of fasteners that you need to use. When we get to transitions and penetrations, there's always a lot of confusion and maybe some contradiction between what manufacturers say, what the specifications say, and what the drawings say, and then you got your shop drawings later. So a lot of times when we go onto construction sites, you'll have in the specifications, hey, install versus manufacturer's instructions, and then there'll be specific things in the specifications that says, do this for these different transitions, which is different than actually what the manufacturer says. So, we always have to follow construction documents, but we are running into the issue where people are going, the manufacturer says this, and then the architect or owner's representatives like, I don't care, this is how I detailed it, and sometimes you run into these issues. So just be careful with that when you're putting together your construction documents and drawings to try to clearly articulate where these lines have to be. And we always say, do the pen test, take your details, put your pencil on it, and just make sure you don't lift up your pencil, because if you do, then you know that you have a breach in your air tightness layer. This is just the summary of things we've already talked about in regards to all the transitions that need to get done. The association doesn't have guide details per se. We are developing some white papers on wall to curtain wall and wall to roof, where we're going to have sample details from an educational standpoint that can just go through, here's some of the things to consider if you have this type of parapet or this type of roof assembly, or if it's low slope or pitched roof or whatever. So we're going to have at least some guidance that you can look at from an educational standpoint to maybe help you develop some of these details. Now, when we look at the installation, it's really going to depend on the type of air barrier that we're choosing. And all of them are going to be within these different types of parameters in regards to, it's got to be this warm, or it has to be protected and can be left out in UV for a certain amount of time. They're all going to be fairly close in regards to what those things are. So the installation is fairly straightforward. If it's a self-adhered membrane, you don't need to be a rocket scientist to go, this thing isn't installed well. Or the same with the fluid applied. It's a little bit trickier to see if it has been installed well, but the common person or pretty much everyone should have the ability to walk through, do a visual inspection, and see if it's leaking or not. Now, it's hard you can't necessarily see the leaks, but you can get a good sense if you see a bunch of fish mouths and unadhered membrane and all that sort of stuff. One issue out of this that we always run into is what happens after we install a really nice air barrier and then we poke a million holes through it because of cladding attachments, because of insulation clips, because of masonry ties, whatever that happens to be. So we do this great job of doing this nice air tightness layer, and then we purposely put a bunch of holes in it. And the question becomes, how big of a deal is that? And sometimes it's a big deal, and sometimes it isn't. And so we get the question, and again, as an association, we want to provide guidance to people. So we've added another research project that we're working on that's actually going to take a look at how much water leakage and how much air leakage goes through different types of fasteners, through different types of substrates, to different types of membranes, self-adhered fluid applied, whatever that happens to be, because it's a big question. And so, again, the intent of the research is to give you some ideas, but typically if you're punching things through, you need to do something to seal it, whether it's a sealant or mastic or whatever that happens to be, or a tie, whatever. you do need to take that into consideration, and maybe it impacts your specifications in regards to maybe the types of screws that you're specifying, the types of masonry ties that you're using, the type of different things used for rain screen systems and thermal bridging. So again, you need to think through these things deliberately as you're putting together your specifications and construction details. Window, curtain wall, and door specs. There is going to be a difference between curtain wall, hollow metal, and flange windows, and there's usually one or two different ways to do it. If you're looking at a curtain wall, the most typical thing I see is you're wrapping your membrane into the rough opening, you're putting your curtain wall in, and then you're making two sealant beads. One is the primary seal for water penetration, and then a seal at the back of the curtain wall to be your air tightness layer. So that we see most commonly. There are different ways that you can actually take the membrane and kind of put it into the throat of the curtain wall frame, and that works too, but it does require a little bit of coordination between the curtain wall guy and the air barrier guy. So there's usually 2 or 3 different options you have for making some of these connections. So you need to determine what is going to be the easiest way from a sequencing standpoint and from a long-term durability standpoint. So the 2 beads of sealants that I've said, that's just what I've seen, not necessarily a suggestion, but that is one of the ways that you can make some of those connections between windows and the rough opening for the curtain wall, or punched windows or hollow metal frames. When we get to some of the quality requirements, we need to take a look at some of the requirements of the people actually installing this. When air barriers started in Massachusetts was kind of the first state to actually require air barriers in their state energy code. And before that, codes kind of talked about air sealing and all this stuff, but it actually didn't say you need an air barrier. So what the state of Massachusetts said is they said, we're really concerned putting these air barriers in because we don't think the industry has the capability or is organized to do it well. There wasn't training, there wasn't this and wasn't that. And then the question was, well, who did it? So in the early days, the people that did air barriers tended to be people that kind of did the same type of stuff on the roof or below grade. So people that did waterproofing, people that did roofing, people that did coatings were traditionally the ones that came in and started doing the air barriers. But back when the association started 17, 18 years ago, there really wasn't a air barrier installer per se, and has been something that we've had to work on in regards to getting the industry up to speed with training and so forth. So the association's put together a quality assurance program. It's completely voluntary. It only becomes required if it's specified. And it talks about having accredited contractors, certified installers, audits, all that sort of stuff. So if you are concerned about the quality of the job, if it's a high performance building, if the owner is going, I want to make sure I meet an air tightness level, you really need to take a look at putting some type of qualifications other than approved by the manufacturer. Approved by the manufacturer means this guy has good credit and can purchase the material, and that could be it. So you have to take a look at some of those requirements for installer certifications. Submittals, usually you can ask for independent laboratory tests to show that these manufacturers meet your performance requirements. They all have it. They can all provide it to you as part of the submittal package. And the other thing that we found to be a huge benefit is the use of mock-ups. And we can go and do testing on not only the air barrier, but part of the roof, part of the windows, the connections to below grade and so forth. And it can become a really good tool to kind of set that standard at the beginning, work out sequencing, work out the quality of installation, and then it becomes this living reference point to go back to say, that's how it has to be done, and the trades are all aware of that has to be done. And there's typically a couple different types of tests that we can do for both air and then water. And most of the time we're doing both, again, with people very concerned about water coming into your building versus air leaking. One of the studies, I think, done by Zurich Insurance that pays out claims found out that 75% of their claims are water related. The other 22% are workmanship related. You put those things together, you got an air barrier that controls water, you got water being your number one issue in regards to claims, you can see why insurance companies are very, very interested in watching how we're putting together our buildings, because they keep out paying millions and millions of dollars. So they're going, how do we reduce our risk and not pay out as many claims? From yourself or from a site QC, there's things that you can do through periodic site observations. You can do adhesion testing. These things are readily available. You can do thickness testing of spray foams, fluid-applied membranes, and so forth. One of the things we find with fluid, the biggest thing in the field, is they're not installed as thick as they're supposed to be. So it's supposed to be 40 mils and it's 20. It's supposed to be 80 and it's 40. That's the number one thing that we find with fluids, is they're just not being installed right. It makes sense. Sometimes, more material equals more money. So if someone hasn't bid it that well, then they'll try to save a little bit of money there. But that's going to be probably the number one thing that we see from the use of fluid-applied systems, which actually are probably the most popular air barrier material being used today. So a couple tests that you can do, there's ASTM E1186. And think of this, putting a plastic bag on a wall, connecting your shop vac to it, putting a pressure, and then going, is there stuff leaking? This is really, it's more scientific than that, but really that's all it is. And then you go around with smoke or something like that to see where it's leaking. So it doesn't tell you how much it's leaking, it's just telling you it's leaking. And then you can go around and see where's it leaking and go, what do we need to do to correct this detail? A lot of times when they're doing this testing, they're doing it over the wall and a window and trying to get as many envelope components together and do the test. The other thing that you can do while you're doing that is you can have thermography done at the same time that will be able to pinpoint where you have air leakage too. And now even, you can get thermography tools on your Apple iPhone, to even check that as it's happening. So we're a big proponent of doing things throughout the construction process to make sure it's being done right and not waiting to the end and hoping that you did a good job. This stuff needs to be done and checked throughout the construction process. ASTM 783, so this is kind of a similar test, but this actually gives you a number. So the other one shows you it's leaking, this one tells you it's leaking this much. So the same type of thing, we're taking an area of the wall assembly, we're kind of segregating it from the rest, we apply a pressure, and then we just measure how much air is leaking through it. So one gives you a number, one visually shows. Me personally, I like the visual one because I can see where it's actually leaking versus having a number and going, okay, now I got to find where the leak is. So 783 is typically the test that's used. You can forego all of that and then just go, I'm going to test it at the end and do a whole building air tightness test. And you can do the whole building, or you can pick just parts of the building to do it. So if you're building a 20-story building, you could take a floor, segregate that floor from the rest of the building, test that. It won't give you a number for the entire building, but it may give you an idea of if floor 3 and 4 are built kind of like floor 2, this will give me a sense of what that air tightness will be. But this is the ultimate, and it tells you how well you did overall. The downside to it, it's at the end, and if it's at the end and you have issues, you have to find where the issues are, and then you might have to start taking stuff off. So I would not leave it to chance to leave it to this. You want to make sure you're doing things right throughout the process to go into this very comfortable. So I'll tell you a little story, and I got just a few more minutes here. So the Army Corps of Engineers for like the last 10 years have been very specific in regards to requiring a certain level of air tightness for energy savings. And it was a big learning curve for the architects involved, for the general contractors involved, because it was new for them, right? Air barriers haven't been around. Well, they've been around for a long time, but they haven't been a code requirement for a long time. And so I got this call from a general contractor one day, and he's like, yeah, we had this, this big fan test done. He's like, yeah, they had all these fans. They did this big test, and he goes, we failed. I said, okay. I said, you failed. I said, like, is this an ABA job or whatever? He's like, no. He goes, we didn't want any type of QA, QC. We're going to do the test we felt we can meet. But now we didn't. He goes, well, what do I do? I was like, well, I don't know why you're calling me. And so he goes, this is what the owner wants. He goes, this is why I'm so desperate to help. So the owner's like, we wanted this, we got this. You need to figure out what that difference is between this level and this level, and then quantify the energy savings for the next 75 years and give them a credit for that difference. So you're at a 1, you're a 3, that's a difference of 2. That would mean using this much more energy for the life of the building, give me a credit. I was like, I am sure glad I'm not this guy. I said, call me back, I want to know how this thing plays out. I never heard anything back, but I thought it was actually quite an innovative solution from the building owner, going, well, I told you to meet this, you didn't, so hey, we'll shake hands, but you need to give me a credit. So anyway, that's probably a rare occurrence that's going to happen, but this gives you a number. This actually tells you this is how well I did. It's not mandatory. It's not used that often. We see the way that the code is going, just like, kind of the buildings are going towards net zero. This will probably end up being a mandatory thing you'll have on every building in maybe the 10, 20 years from now. Right now, there really isn't an infrastructure of people that know how to do this well. So if everyone in this room started requiring this, you probably wouldn't have enough people to even do it. There's only a few people across the country that would really be deemed experts, so there's this kind of lack of infrastructure of people qualified to do this. There also isn't any qualifications to do this. So if you decide to go buy some fans from Minneapolis Blower Door, because one of the main manufacturers of whole building air tightness testings in Minneapolis and has been around forever, you can do the test. That's not an issue. But I can go to Home Depot and pretend I'm a carpenter. Doesn't mean I'm a carpenter. My wife will completely attest to that. That's why I teach versus doing. The rest of my family actually does construction. I teach because I'm not very good at it. So just something to keep in mind. So in conclusion, because I have literally 3 minutes left, proper specifications is kind of where things start. And the more articulate we can be and the more deliberate in regards to the language we use will just help the project get off on a better start. Again, we don't want to just worry about air permeance of that material, that very basic peanut butter thing. Let's just pretend that doesn't exist and go to the assembly testing. So that 2357 assembly test, please, please, please consider having that as a minimum required in your specifications. Otherwise, peanut butter, jelly, and bread, hey, contractors are very sneaky sometimes. They'll find a way to meet code. And so, is there any contractors here actually? Damn it. I'm joking. I know you would never do something like that. We have to think about our materials, where we put them in our wall, and really consider that this one material that we're using is doing a whole bunch of things and doing one of the most important things that's buried in our wall. So the more that we can do to have good specifications, good quality control, good functional testing throughout, good people that are doing that, and good coordination will help us go a long way to meeting our design intent, to meet energy code requirements, and ultimately just to have a good building that performs. There's been a lot of research done on LEED buildings, and some of the LEED buildings that we've gone through are the biggest energy hogs. LEED Platinum energy hogs, depending on how you pick some of your points. So just because someone says it's a green building doesn't mean it's a green building from an energy standpoint if you're doing these other things. So this is where we're going in the future, and this is something definitely that's important.